So we're going to study in this lecture, in this multiple part lecture, how to solve homogeneous linear systems with two equations and two unknowns. You already probably went over, you should have went over the finding the eigenvalues and vectors in a square matrix as part of your linear algebra course, which should be taken at the same time or before this differential equation class. But let's actually review briefly the mechanics of finding the eigenvalues and vectors of a matrix. And after we do that, after I go walk with you through these linear algebra stuff, we're gonna go over an example to make the connection between eigenvalues and vectors and solutions of homogeneous linear differential systems, because it may not be obvious why in trying to solve linear homogeneous systems you will arrive naturally to the concept of an eigenvalue and vector. And actually it's quite interesting, it's useful, very useful to make that connection, because I hope it will justify why actually you care about certain topics in linear algebra that may not be obvious in terms of what they are good for. Of course, differential equations are not the only justification for linear algebra, but that's one of them. So one of the uses of some linear algebra concepts. So let's go over a couple of notations. So if you have a square matrix A, to find the eigenvalues and vectors, basically you go through two steps, right? You set up the so-called characteristic equation, which is the determinant of A minus lambda times the identity matrix. So big I in our notation here stands for the identity matrix, which is 1, 0, 0, 1 in the 2 by 2 case. So you set this determinant equal to 0, and you'll see there is a good reason in the context of differential equations why you do that actually. So then you try to find lambda, I mean the so-called eigenvalues. And then you have, of course, a couple of situations. In the 2 by 2 case, you can have distinct real eigenvalues, a double real eigenvalue, complex eigenvalues, and so on. Then for each lambda, you're going to find a corresponding non-zero vector. Keep in mind this, you're looking for a non-zero vector. By 0 bar, I mean the column of zeros, right? 0, 0. Such that A minus lambda I times V bar equals 0. So this basically becomes a system of an algebra system in the entries of the vector V. So for each lambda you're going to find a non-zero vector. If your algebra, if your computation is correct, this system always leads to infinitely many solutions. You just need to extract one non-zero solution for our purposes. So things will be actually very easy in the 2 by 2 case. All you have to do is to extract a non-zero solution, and that constitutes your eigenvector. Just as a side observation here, when you say the eigenvector is a misnomer, because as I mentioned before, this will always have infinitely many solutions. So there are infinitely many eigenvectors corresponding to the single eigenvalue. What you basically provide is the basis of that eigenspace. So I mean the basis of the vectors that satisfy this system. So basically in the 2 by 2 case, in the vast majority of time, essentially you provide a non-zero solution of this system. So moving on, this setting in the 2 by 2 case looks like this, right? To say that you subtract lambda times the identity means you take out lambda from the main diagonal of the matrix, set up that determinant equal to 0, and then you solve for lambda. I want to point out to this shortcut here, this formula, because you save some time if you start with this. So if you set up your characteristic equation to find lambda and walk through the computation here, and write down the quadratic in lambda, you will notice that the coefficients of lambda are very precise, and I mean are related to the original matrix A. So for one thing, the constant term is going to be the determinant of your matrix, and the coefficient of lambda is minus A plus D, which is the sum of the elements on the main diagonal, also known as the trace of a matrix. So you might as well just remember this format when you start finding the eigenvalues. Lambda squared minus, there's a minus as part of the formula, minus the trace being the sum of the main diagonal, plus the determinant. So I'm going to use that just to save time from now on. Of course, if you forget this shortcut, you have to start from here and then walk through those computation to get lambda. And then for each lambda, you're going to find your eigenvector, which comes from this linear system. We're going to have multiple eigenvectors because you have multiple eigenvalues. I will always call the entries v1 and v2 for these different eigenvectors because, you know, when you solve the system, you can actually put numbers on this one. So these are just like placeholders. v1 and v2 are just notations for the first and the second component of a given eigenvector. I'm mentioning this because, for example, if you have two eigenvalues, I'm going to use this notation for the eigenvalues and the eigenvectors. I want the index to indicate which eigenvalue I'm referring to. So if I find the lambda 1 an eigenvalue, v bar 1 will be the eigenvector. But in the process of finding this eigenvector, I may use v1 and v2 as default variables for the entries of that vector. So with that preparation, let's actually see why we have these eigenvalues and vectors popping up in the process of finding solutions of a homogeneous differential system. So let's start with an example that we did last time. Suppose you want to solve, and let's write it by components this time. Suppose you want to find the solution of x prime equals x plus y, and then y prime equals 4x plus y. Which of course in the matrix form is 1, 1, 4, 1 times x bar, right? The column of the dependent variable. So you might remember when I said that, you know, if you look at the homogeneous system in the matrix form, this is kind of analogous to the exponential or the, right, in the single differential equation case. Okay, so, and remember that one, which I asked you to memorize, right? I mean, the solution of that is an exponential. So this will be c e to the at. So it's not actually that far-fetched to imagine that your system also maybe have an exponential solution, given the fact that basically the matrix form, it resembles the single equation, the single exponential ODE. And in general, I mean, if you have homogeneous linearity and then all constant coefficients, it's a natural way to ask whether actually the system will have an exponential solution. Another thing to keep in mind, we're looking for the general solution because a particular solution is very easy to find. I mean, it's 0, 0, right? I mean, the trivial solution is obvious, right? I mean, and that's also the equilibrium point. If I plug in 0 and 0 for x and y as functions of t, clearly I get a solution for the differential system. So from this point on, I'm looking to find a way to figure out the general solution, and by default I'm looking to find non-zero solutions, so other solutions besides the trivial one. And remember what I told you before, eventually we're going to have to find two independent solutions. It is a fact proved, you know, that the dimension of the solution space is 2 in this case. So you need two independent solutions for the system, two non-zero independent solutions to be more precise. So keep that in mind, we're looking for non-zero solutions of this differential system. And if I'm looking for these solutions in the form of an exponential, then let's actually choose that type of format and see if we can actually find the recipe of finding these solutions. So let's look for solutions in the form of for x of t, let's write it here, so in the form of x of t equals v1 e to the lambda t and y of t v2 e to the lambda t. Okay, so I'm using obviously lambda on the exponent because I'm anticipating already that, you know, that exponent will have to be an eigenvalue. I just want to show you that it has to be an eigenvalue if you're looking for solutions on this form. One thing to point out also is that the reason I choose the same lambda, so I choose different coefficients, v1 and v2, these are constants, because I don't know which of these coefficients will fit my system if I look for solutions in that form. But I can tell already that lambda must be the same if I want to have a solution. Because remember, if you differentiate e to the lambda t, you still have e to the lambda t. So probably these two guys combined should have the same exponential if I'm hoping for that exponential to cancel. I mean, if I'm hoping that these two are solutions, it's not that hard to guess that for each independent solutions, lambda has to be the same. So notice at this point, really the question is, how do you find three quantities, lambda, v1 and v2, such that these two guys, x of t and y of t, form a solution? So keep that in mind, that is the question. Can I find these three quantities such that I have a non-zero solution for the system? There's only one way to figure this out. We have to plug in these functions into the system and hope we get a method of finding these three quantities. So if I plug in x of t on the left side, I have to take the derivative, so that becomes lambda v1 e to the lambda t. X is v1 e to the lambda t plus y v2 e to the lambda t, and I can pull out e to the lambda t, and that's, again, remember the reason why we chose to be the same, these lambdas. And on the left hand side, again, for y prime would be v2, so lambda v2 e to the lambda t, 4 times v1 e to the lambda t plus y, which is v2 e to the lambda t, and again we can pull out e to the lambda t. And as you notice, from left to right, we can divide e to the lambda t and cancel it out. Okay, so now look carefully what happens if we move all the stuff to the right hand side. So I move this guy to the right hand side, and if I combine v1s, so I can get 1 minus lambda as a factor. Yeah, so lambda v1 to the right hand side becomes minus lambda v1. And here I copy for v1, and again lambda v2 move to the right hand side and pull out v2, and I get the coefficient 1 minus lambda v2 equals 0. So I hope you can see how the eigenvalue concept pops up at this point. Okay, so pause for a moment to understand what happens here. So basically, these lambda v1 and v2 must satisfy the following linear system, algebra linear system: 1 minus lambda 1, 4, 1 minus lambda, and then v1 and v2 with 0, 0 on the right hand side. So this becomes essentially a linear algebra question. To find a non-zero solution in that form amounts to find a non-zero solution of this linear system. Remember, non-zero solution. I want to find a non-zero solution of this system because, again, not a surprise, if you plug in 0 and 0 for v1 and v2, this will be true for any lambda. But then how do I get a non-zero solution? This is the time to actually remember and dig deep into the linear algebra stuff you learn. And remember, perhaps one of the dense statement in linear algebra is the statement determinant of a matrix not equal to 0 or equal to 0, but let's say not equal to 0. There are so many meanings to this statement. So for example, what did you learn about in relation to saying that the determinant of a matrix is not equal to 0? Well, you hopefully learn lots of things, right? I mean, for example, one consequence is that the matrix has an inverse, or the columns that form the matrix form a basis in the space in Rn, or R2 in this case, because we have a matrix of 2 by 2. But one important consequence of this, of the determinant not being equal to 0, which is relevant to our case, is that if the determinant is not equal to 0 of a matrix, the solution, let's write it here. So if you look at the determinant, so if you look at the system, right? Let's write it actually in the context of our system here. So if the determinant of this matrix would not be equal to 0, one consequence from linear algebra is that the system that we see here has a unique solution. So this implies unique solution. but the unique solution has to be 0, 0. Okay, so I know already that the system has a 0, 0 solution. If this system will have a unique solution, then that means you would only have v1 equals 0, v2 equals 0 as a solution. This is exactly what we do not want. Right? We want a non-zero solution. And that is the reason why we set to begin with the determinant of this matrix exactly equal to 0. So that is the starting point in finding eigenvalues and eigenvectors. That's out of range, sorry. So that's the starting point in finding eigenvalues and eigenvectors, but it's also the starting point in our context in finding a solution of the differential system. The reason we do this is because we're looking for non-zero solutions eventually of this system. So we already have the framework essentially. I get a lambda, an eigenvalue, which in my context means it will be the exponent of e to the lambda t. I'm setting this determinant equal to 0 because I'm looking for non-zero solutions of this system. Once I find the lambda, I plug it back here in, and I'm going to extract the non-zero solution. Now again, one consequence from linear algebra is that if the determinant is equal to 0, not only you have non-zero solutions, you're going to have infinitely many solutions. That's why you have infinitely many eigenvectors for a single eigenvalue. Your job is to extract the non-zero eigenvector. Now in the vast majority of cases, there's only one of them because the eigenvector depends on arbitrary variable, typically, in many examples. So therefore, the basis of the eigenspace is 1, so you produce just one non-zero solution. There is one special case which I'm going to mention just for completion of the theory, in which you could have a single eigenvalue and of course and two eigenvectors. That can happen in the 2 by 2 case. For larger matrices, of course, there are more combinations, right? I mean, the eigenspace for a given eigenvalue can have various dimensions. You may 1, 2, 3, and so on, depending on how large the matrix is. But for our 2 by 2 case, there is basically one case when you can have a single eigenvalue and two eigenvectors, because the basis of the eigenspace is 2. But you will see that in the context of solving ODEs, that's actually quite a trivial case. You don't actually have to solve it via systems. We're going to go over it briefly just to mention it, that it exists, to be aware of it. So at this point, let's actually find what lambda is. In fact, we'll do that maybe in the next part. So we're going to basically finish the solution of this system, because in this particular case, lambda will have so the characteristic equation for lambda will have two distinct real roots. So we achieve our goal to produce two independent solutions, because we're going to have two different lambdas, two different eigenvectors. So let's continue with the second part to actually finish this example, and then we'll move on with the other cases. Because the reason the lecture is a little bit longer is because we have several cases to deal with, real eigenvalues, different, equal, complex eigenvalues, and so on. So stay tuned for the second part.